Hi, my name is Shubham, and today I'm presenting the machine learning workflow designed to modernize ABC Bank's credit approval process. So currently, the bank relies on manual reviews, which are slow, expensive, and prone to human bias. My objective was to build an automated classification model that can predict whether an applicant is a good or bad credit risk. So the metrics that we utilize are AUC, area under the receiver operating characteristic curve. So this lets us know whether a model is good at, evaluating whether binary classifications are positive or negative. So this ensures the model ranks customers fairly. There's also accuracy, which is important for basically making sure whether the approval or denying process was accurate. Precision, which is important to make sure applicants weren't incorrectly approved, because this costs the bank a lot of money. And recall, which to make sure that the applicants weren't incorrectly denied, because that could also cost the bank a lot of money in terms of lost opportunities, but it could also cost the bank a lot of monies in terms of liability and lawsuits that could come with it. So in this assignment, we'll be doing data processing to make sure the data is clean and usable, feature engineering to make sure we have manipulated the data enough that it doesn't affect our models negatively, model development and evaluation. So this is where we train and try out different types of model and compare them. And finally, we'll give some recommendations. So first of all, you need to download some necessary libraries, which will be useful for us. So some libraries like AutoViz, AutoML like H2O, and basic manipulation libraries such as Seaborn, Pandas, NumPy, etc., and sklearn, which will be important for creating the machine learning models. So first of all, data exploration and cleanup. So I started with a data set of 900, not, no, 9,709 applicants. Um, and there were 20 different features. So you can look at the data set and see the different features over here. So these are the columns and these are the rows. So after doing an exploratory data analysis, this helps us understand whether there's missing values, whether there's skewness in our data, etc. So as you can see, there were no missing values, also no duplicates. And these are the unique numbers, unique values in each of our features. So the two lets us know that these are probably a binary feature or like a category. Five, these are probably also categories, and it basically helps us understand the type of data we're dealing with. Also, the df.info will also tell us the data type. So using AutoViz, we created some graphs that will help us understand the issues associated with these data. So as you can see, there's also like data quality issues that the function automatically gives us. So it says there's like 31 outliers. So there's a lot of outliers in these, especially like income, number of children, number of family. These outliers can skew our data set by a big amount and actually like make influence our outcome in a not so positive way. So we're going to have to fix all of these issues over here. And there's also some rare categories. These basically means these are like categories that are only used by a few like applicants. So you could either like get rid of these categories or you could compile them into one other category. Um, okay, so these are the descriptive statistics. You can have a look and go through them. And also the skewness. So this is one of the most important findings of our exploratory data analysis. So you can see there's like a income has a skewness of 2.6, which is extreme. It is very high. There's also skewness in number of children. So these skewness can really, really affect our outcomes later on. So let's process this. So how do we try to fix this? So first of all, we'll drop the ID because ID is really not necessary for our model because it adds no meaningful information. We'll also like try to encode our features. So we will use a label encoder for that. So this basically like encodes categories into like 0, 1, 2, 3, 4, 5. These are equal and they don't have a meaningful hierarchy. So you see over here, there's one that means there's two types of property ownership. You own it or you don't own it. It's the same for like, let's say income type. There's four over here. That means there's probably five different income types because it starts from 0. So to fix the skew, we try a few different things. First of all, we can also try, for example, changing the type of data. So for example, changing for total income, we try changing it to a logarithmic scale, um, etc. So if you look at it again, you can see that the skewness has dropped considerably. So in the data quality issues, you can see that although there are some outliers, the skewness has greatly decreased. So next part is we have to split predictors and targets. So what does that mean? That means we're separating the X, which is the variables or predictors or whatever you call it, and Y, which is the target or the outcome. The Y is a binary outcome. It's 0 or 1. It's yes or no. It's approve or deny. While X could be multiple, depends on what we decide to use and what features each of our models use. So we do a PCA, a principal component analysis. So this helps us properly like examine each of the components in our models. So as you can see over here. So this is the cumulative explained variance with the number of components. So as you can see, it's an upward curve. Higher the number of components, the higher explained variance. The original processed feature importance. So we'll use the entire dataset to generate feature importance number. So we can use standardizations such as z-scores. This helps us to make sure that our data is standardized. It's normal and easy to like use. There's also feature importance. So there's some algorithms that you can use to check the importance of the features. As you can see, age, income, account length, years employed. These are one of the highest importance with the features. So now we start developing our classifiers. So we train classifiers on our process dataset and we evaluate their performance, investigate the effects of certain data processing, and we compare them. So first we'll have to split our datasets into training and testing. And then every time we create a classifier, we test it using cross-reference methods. So first, we also compare a few different types, like processes. For example, we compare regression and random forest. The random forest is basically an ensemble method for decision trees, and regression is basically a linear regression model. So as you can see, this is the regression model and this is the random forest model. They both have very, very similar accuracy. No, in fact, they have the same accuracy. So there is no difference. Um, we can also compare it to binary encoding, and we can compare it to label encoding. In this case, also we can see that it's very similar, and there's basically no difference. But you see over here, 0.85, 0.85. There's basically no difference. The comparison with and without k-means clustering. So we did the same thing, and we can check over here the difference. So if you look at the deltas, it's almost negligible. It's almost none. So this means that random forest with clustering versus without clustering, and logistic regression with and without clustering, almost the same outcome. So now we will use H2O. This is an AutoML algorithm that gives us a list of the models we can use in this case to check which model works the best. So we have to do some manipulation to make sure that the model works great and create some lists to put the new store the new metrics and a leaderboard where you can see all the different models. So this is the output we have. So the H2O AutoML generated 16 or 17 different new models. And there's the AUC, accuracy, precision, and recall for all of them. So you can see that the AUC is pretty poor for most of the model, with the highest AUC being in the first one, GBM5. The accuracy is 88%, precision 68, and recall is 0.38, so 38%. As you can see, there are other models with higher accuracy, like this one with 95%, or even this one with 98%. But look at the AUC. The AUC is much, much, much lower than the first one. And in terms of fires, AUC is way more important than accuracy or precision. So we do lose some precision, accuracy, and recall, but this one has the highest AUC, meaning it's the best at classifying good classifiers with bad classifiers. So this is the model we will be using. Um, so there's other things that I'd like to talk about. So we haven't changed any of our columns, but sometimes it's important to choose which variables you'd like to include and which variables you would not like to include. For example, gender. So gender is a legally protected class that if you do include in a bank or a financial institution, you could be liable for discrimination. So gender, age, sometimes even like housing types. There's so many other ethical considerations for creating a ML model, especially for something as important as a bank. And the conclusion and final improvements that I'd like to make is that um, basically ABC Bank should deploy the GBM5 model. Even though, according to industry standards, a 0.57 AUC is pretty low, it is the highest. And the root cause is because our data set is purely demographic by age, job, car, whatever. And we're trying to predict financial behavior without saying financial history, which is probably way more important than lifestyle factors. So to improve this model, the next iterations must integrate behavioral data such as maybe credit scores, debt to income ratios, and payment history. So that is all for today. Thank you very much for listening.